Hello and welcome to my channel. My name is Bennett and this is video 1. A little bit of background. I'm an undergraduate student studying for a BS in applied math. This channel will be used for my tutoring company in order to offer some additional online resources, as well as sharing some interesting challenge problems that I've come up with and collected over the years. I'm also currently working on a text on integration techniques, so a lot of the problems on my channel will be related to integration and integral calculus. Now please bear with me as I am still learning how to use this virtual whiteboard software, but I think I'll get the hang of it pretty quickly. And as I say that, there we go. And clear that out. Back to where we were. So today, video 1, we're going to start with some U-Substitution. Now I very well may go back and do the whole limit definition of integrals, as well as all of the differential calculus that is commonly seen. However, for today we're going to jump right in on the channel and start with some relatively easy U-substitution problems. So number 1, let's look at the integral of sine of 5x dx. Now we know from differential calculus that the derivative of cosine of x is equal to minus sine of x. So this is kind of the relationship that we're looking to use here. However, we have a 5x instead of an x, and we have a positive sign instead of a minus sign. So this hints to us that we may want to use a technique known as U-substitution. And in this case, we would say u is equal to 5x. Now in order to evaluate this integral with just a sign of some variable, we need to take the derivative of u and subsequently the derivative of 5x. We can't take the derivative of just one side. So we now have the relationship that du is equal to 5 dx. And we just get that from the basic derivative rule where you do d over dx of some constant times a function, and you're just going to get the constant, assuming that function is order 1. So really it would be better to just go ahead and write this as cx. So we gain that relationship there. So now going back to our integral, we can plug in and notice here that dx is now 1/5 du by dividing 5 on both sides. So really we're left with the integral of 1 over 5 sine of u du. Now based from basic integral properties tell us that we can bring out the 1/5 because it's a constant, and now we're left with the integral that we were looking for. And if we go up here, we can kind of do the antiderivative of both sides in order to see our relationship more explicitly. The antiderivative minus sine of x is cosine of x. Now here we have positive sign, so we just need to add a negative sign. So we get negative 1/5 cosine of u. Now we don't know where on the graph this function lies in terms of adding or subtracting a constant. So because it's arbitrary, we need to add c. Now if this was a definite integral, or an integral of the form a to b f of x dx, then we would have some exact solution and there would be no ambiguity of where it lies on the graph. But that's not the case here, so we need to cover ourselves just in case with our plus c. Now, substituting back in, into our expression, we have minus 1/5 cosine, but u is really 5x. That's how we defined it, plus c. There's our final answer. Now, let's go ahead and move on. That was a pretty easy introductory problem. So let's move on to something slightly more abstract, but still in the elementary area. So let's look at the integral of x plus 3 to the power of 17 dx. Now as you do more and more U-substitutions, you'll get a feel for what the substitution should be. Oftentimes when you have some kind of a grouping symbol like parentheses, you'll simply want to make the U-substitution whatever the expression is inside of the parentheses. And as the problems get harder, the U-substitutions will be less and less obvious. But for these introductory ones, we'll simply make u equal to x plus 3. Now we need to find our new differential, which will be du. So once again, we get the relationship. Now here, unlike last time, du is simply equal to dx because the derivative of x is just 1. It's just the constant in front. So we go back to our integral and we plug in u to the 17th and we simply have du. Now we should know the power rule, and the antiderivative of a power function, say we have some f of x and it's equal to x to the n. Well, the integral of f of x is simply equal to 1 over n plus 1 x to the n plus 1 plus c. Now this is more or less the opposite identity we get from differential calculus, where if we have f of x equal to x to the n and we want to know f prime of x, then we simply multiply the exponent in the front and subtract 1. So you see up here we added 1 to the exponent and then divided. So this is the power rule, and this is what we're going to use to evaluate our integral. All right. So we're going to add 1, and then we're going to divide by our exponent. Once again, do not forget your plus t. We don't know exactly where this function lies on the graph because it's an indefinite integral rather than a definite integral. But we're not done because we want to finish the problem out in the same variable that we started with, which is x. So we need to plug back in for u equals x plus 3.